It's time for our second form of energy. The last video was on kinetic energy, and so this video is now on potential energy. And so we're going to, again, try to relate this back to work, because work is another way that we, or I should say the first way that we started to calculate energy. Okay, because remember, we have to do work, and in order to do work, we use energy. So I like to kind of go back to 9th grade, okay, and I know that some of you are like, oh, not 9th grade again. Well, here's what we did in 9th grade. We taught you about potential energy, and again, we were giving you a formula, and it was mgh, and this is what you were expected to do. So again, a sample problem from 9th grade science would have been to look at this rock. Now I found this picture, of course I just looked for rocks on cliffs or something like that, and this is the first one that came up. I like the picture. There's lots and lots of pictures of this particular rock. I think it's in Arches National Park. So it's something that you can kind of go through and look at. And I just chose this one because, again, I thought it was kind of nice. It followed rule of thirds for those of you that like to look at photography. And it was a very nice coloring to the sky, so that's why I chose it. Anyways, I'm estimating that the rock has a mass of 10,000 kilograms, and it's perched on a cliff that is a height of 200 meters. So we're now looking for what is the potential energy of this rock, okay? And this is the rock part that we're talking about, and this is the cliff. So we're looking at this being our height of 200 meters, and our mass is, again, 10,000 kilograms. So I know my M, I know my H, and H is nothing more than a distance, by the way, so just keep that in mind, distance, displacement, height. We know that G is on this planet 9.8 meters per second squared. So if we want to just find our potential energy, all we have to do is say, put M, which is 10,000 kilograms, times G, which is 9.8 meters per second squared, times the height, which is 200 meters. So you grab your handy dandy calculator, and I'm going to turn it on, and we got 10,000 times 9.8 times 200. We get an extremely large number of 1,906, and 1, 2, 3, 4, 5, and that would be the units of joules. Okay, and again, how do I know that this is joules? Well, it's a kilogram, it's a meter, it's a per second squared, and it's a meter. And by the way, this times this was nothing more than our force due to gravity, and this is nothing more than a distance, and a force times a distance is nothing more than work. All right, so potential energy is really just work, but we think of it in the other sense. Okay. That's a lot of joules, okay? We're looking at 19 million joules. And again, in the last video I talked about how joules are so small, and typically what we would do is we'd look at joules and we'd say, let's make it kilojoules, okay? And so then we could convert that, and remember that a kilojoule is bigger than a joule. So in other words, we're still at like 19,000 kilojoules. An interesting thing would, of course, maybe be to convert this to, say, the energy that we consume, and you guys know about energy consumption in food, which is calories. So I could convert my joules to some science calories, and in 1 science calorie there's 4.184 joules, and then in my science calories to my food calories, in 1 food calorie there's 1,000 of these. And so that would tell me how many food calories I'd have. So if I did this where I divided by 4.184 and then I divide again by 1,000, I end up getting like 4,685 calories. So in other words, it's like 2.25 days worth of my allotted daily calories it would take if I actually lifted that boulder up. So again, how did the rock get up there? Somebody had to put it up there, right? And if there's somebody that's putting it up there, then they had to do work. So again, potential energy, work are kind of the same thing. It's just the way that we look at it, okay? If the rock was on the ground, we had to put it up, we had to do work, okay, work against gravity. Once the rock is up there, it has the potential to fall due to gravity, okay? And again, we do call this form of potential energy a gravitational potential energy. Okay, so that was our gravitational potential energy. Now there are other forms of potential energy, and in a chemistry class you probably learned about chemical stored energy. So in other words, an atom is connected to another atom via a bond, and that bond represents the amount of energy that's holding those two atoms together. And the moment you break that bond, you have the ability to release that energy and use it. Well, in physics, we have other ways that we look at energy, and this is kind of a more mechanical sense. We look at elastic energy, okay? If you remember back, we just got done doing a lab with springs, where we were looking at the force that's variable for a spring. So in other words, you stretch a spring, the force changes as the spring is stretched, okay? So it's a relationship between the force and the displacement of the spring. Well, the same is going to be true when we start to look at the elastic potential energy, okay? So elastic potential energy has a relationship. It's 1/2 the kx squared, x being the displacement of whatever is being stretched or compressed, okay, and the k being the spring constant, or the essentially our elasticity constant. In the case of our guy with the slingshot, so it looks like he's pulling back on a slingshot and he's going to release it, okay. So springs they don't have constant force, and this is why we have to study our potential energy different. Okay, so, I'm back. Had to sneeze there for a second. So anyways, we were talking about elastic potential energy and how the force for a spring or for a rubber band or for anything elastic is not a constant force. I'm just going to draw a quick little graph here. So again, if you remember when we talked about force and work, we looked at it from the sense of, if I graph my force versus my distance, under constant force, I get something that looks like this, and then I can find the area underneath that, and the area underneath represents my work. Well, now in a spring or in a non-constant force, most of them are somewhat linear. When we graph our displacement, and now I'm going to switch from calling it d to x because I want to follow my notation because they're talking about x being the distance, versus force, we see something that looks more like this. So again, it's the area underneath here that represents my work. Well, now this is nothing more than a triangle. So in other words, this thing right here looks a little bit triangular. Now you got to remember that when we talk about force for a non-constant type situation, our force of our springs was equal to a minus kx. Okay, so in other words, that was a function that we used. So in other words, we got f values based on this, and we got our d value or our x value based on this. And so in other words, if we look at the area underneath here, the area is nothing more, so the work or the area is nothing more than the minus x of x, or k of x. That's my force. It's 1/2 because it's a triangle times that, and so that's how they end up getting this as my, remember, potential energy is equal to 1/2 kx squared. We drop the sign, of course, when we start talking about our work and our potential energy, because remember that energy is a scalar quantity. It's a scalar quantity. It doesn't necessarily have value. Even though work could be negative, so we could have negative work. But that's typically the case, is that we're always talking about it in terms of a scalar sense. So in other words, potential energy is always a positive number. We lose some potential energy, we gain something else, because it's a transfer of energy. All right. So now let's look at a typical problem involving elastic potential energy. So now I have my bridge and I have a bungee jumper. Okay. Never bungee jumped. Sounds like fun. I think that I like the idea of jumping out of an airplane better than I do jumping off of a bridge and hoping that that cord holds. There's always the issue of, did they measure things correctly? And that gets into my whole issue on significant figures. But different discussion, different day. So anyways, I have my stunt man, and he's attached to a bungee cord, and the unstretched length is 15 meters. Jumps off the bridge. The height from the bridge to the water is 50 meters. Okay, so from my picture here, here's my person. Okay, from here down to the water, that's 50 meters. All right. When he finally stops, the cord is at a length of 44 meters. So in other words, he's jumping, he's going to stretch, and this is his stop position. And from here to here, it's 44 meters, but from here to here, it's 50 meters. So in other words, he has a little bit of height above the water. Doing my quick little math here, the distance between there and there, 50 minus 44 is only 6 meters. So in other words, he's 6 meters above the water when the bungee cord is done stretching. Now, we're going to assume that there's a spring constant. Okay. There's that K value. Notice that's in Newton meters and newtons per meter, and that works out. It's a constant. We just want it mathematically to cancel what we need to cancel. We're looking for the total potential energy relative to the water. So in other words, he's going to have two forms of potential energy. He's going to have potential energy right here. We're going to call that the elastic. And then he has gravitational potential energy here. GPE, gravitational potential energy there. So in other words, we're going to add those two pieces together, and that'll give us our total potential energy when we're looking at the bungee jump. Okay, so let's tackle our elastic potential energy first. And if you remember, it's 1/2 kx squared. Okay, so that's all we have to do, is we have to look at it in terms of that. I know my K value, 71.8 meters, newtons per meter, times our distance, which is going to be 44 meters. We're going to square that, and that'll give us a value. So I'm going to grab my calculator. 5 times 71.8 times 44 squared, enter. So I get like 69502 joules here. My GPE is going to be based off of this little bit of a height. So in other words, I know the mass is 70 kilograms. I know my gravity is 9.8 meters per second squared, and I know that my height was 6 meters. So I just take my 70 times 9.8 times 6, and I get 4116 joules. I add them together, and I get my total potential energy of 73,618 joules. Okay, and so that's how we look at potential energy. Okay, different forms of it. I think I'm going to go refill on a little potential energy at this point in time. Maybe a chemical form. I've got some candy corns that I think I might munch on. All right, we'll see you in the next video.